What is up, YouTube? Welcome back to another episode on CodeWithAni. Apologies for this delay. There was some personal work that I had to attend to, but we'll start this series now properly. I've already shared the roadmap with you guys in one of the videos, earlier videos. So from here on forth, we will follow that roadmap and let's get started with this particular video. So here we're going to talk about the asymptotic analysis and notations. Now this is the core concept behind the analysis of the algorithm's efficiency. And this is one of the first topics that is usually taught when you step into the world of data structures and algorithms, because to understand the algorithms, you also need proper ways to measure the speed with which the algorithm executes and the amount of memory that the algorithm can take. So asymptotic analysis can give you the answer to that, and let's see what this term actually means. So whenever you have a equation, right, some linear equation like let's say 3n cube plus 4n square, or let's say just 3n cube plus 4n, right? Pardon me, this is actually n cube, not n3. So it's 3n cube plus 4n, and when you take a large value for n, right, what this approximately becomes is 3n cube also roughly translates to n cube. So for very large inputs of n, this 4n is basically negligible, and the 3n cube basically becomes approximated as value n cube. So this entire equation asymptotically becomes n cube, right? So this property of generalizing very large values of n into a particular equation like this one is called as asymptotic analysis, and it gives you a very large input size response, like what will be the result when you have very large values of n, and this is the approximate value it will point to, something like it tends to infinity, right? So similar to that, any equation can be asymptotically converted into something like this, right? Now when we delve into the notations that are available to measure these, there are three basic notations that people use in the world of algorithms. One is called as big O, usually represented as this capital O, and then you have big omega, usually represented by that omega symbol. I'm not sure if I can bring that up on the keyboard, but I can probably draw you and show that here. I also have the pen and paper input set up here because this particular series requires some graph. So this is called as omega. Okay. Likewise, you have another one called as big theta notation. Okay, and big theta is nothing but this one. If you remember theta from your mathematical equations, this is what is theta. Okay, and this is omega. Right. So what is the purpose of these three representations, right? So one of the representations, basically the big O representation, is called as the worst case time complexity. Worst case meaning that is the maximum amount of time that the algorithm can take to execute, or that is the worst possibility, basically value of n, which is the largest value of n, and that is the worst case time that the algorithm will take. For example, let's say where you want to reach a particular location, you say that based on the traffic, the worst case possibility is I can reach at, let's say I start at 12 p.m. I can reach at 1 p.m. right? When you mention it in that way, what you basically refer is 1 p.m. is the maximum time by which I would be present. I can be present before that, but that is going to be the worst case time it is going to take for me to commute. Likewise, for the algorithms world as well, you have something called as a worst case scenario. That is the worst case amount of time the algorithm takes to execute, and that is represented by the big O notation. Then you have the big omega notation, which is basically the best case time complexity. Now best case obviously is the exact opposite of the worst case, because best case I can say that, let's say I start from my home at 12, I reach by 12:20 based on the traffic conditions. That is the best case possibility. Worst case, I'll be there by 1 p.m. Best case, I'll be there by 12:20. So same way, for an algorithm, the best case running time, that is the quickest the algorithm can run, is represented by the big omega notation, or the best case time complexity. Then you have big theta, and as you could have already guessed, if you have already guessed, it's the average case time complexity. meaning this is the average amount of time the algorithm will take. Let's say I can reach by 12:15. Worst case, I'll reach by 1 p.m. On an average, I can reach by 12:30. So that is called as the average case, right? So same way for an algorithm as well, based on the number of inputs, big theta will give you the average case time complexity, or the average running time for the algorithm, right? So these three are quite important, and the most predominantly used notation is the big O notation. The reason being, most of the time we are only interested in the worst case scenarios, right? We don't usually care much about the omega and theta, because the best case and average case will anyway happen, and worst case is what we usually look at, because if we see that worst case itself is satisfactory, then we don't have to worry about the omega and theta notations, because if worst case is something that can be handled by your system, or if you're okay with that time, then obviously theta and omega fall within the radar, so there should not be any issues. Now, if you want to represent these graphically, how we can tell is, let's say there is a function f of n and there is a function g of n, okay? Then if f of n, okay, is less than equal to g of n, okay, or c into g of n, for some value c, for some constant c, okay, and all values n greater than some value x, x can start at 0 or x can start at any other positive value, and it goes all the way, then this representation is called as, or it can be represented again as, f of n is equal to big O of g of n, right? So for all values of n, your f of n function is less than equal to c into g of n, because your g of n is called as the upper bound, basically, right? Upper bound in the sense that is the worst case time complexity. So graphically, this will look like, let's say, right? And now this is, for example, f of n, then this will be, okay, 1 minute, g of n, and this is f of n. Now this is called as the big O notation, okay? So all values of g of n will be greater than f of n, provided it's multiplied by a constant c, and that will always be holding truth, and that is called as the worst case complexity representation in graph. Same way for the other one, which is the big omega notation, f of n is greater than equal to c into g of n. Same way for some constant c, n greater than some value x, x can start at 0, can be 0 or more, okay, or any value more than 0, right? Same case applies here as well, and that's when you will say f of n is equal to omega. I am not able to represent that here, I'm just saying omega of g of n, although it is that symbol that I showed you here, right? Omega of g of n, okay? So that graph will also look similar to this, but the only difference being, in this particular graph, let's see if I'm able to draw it here. In this particular graph, you have two equations like this, f of n and g of n, but in this case, this is going to be f of n and this is going to be g of n, because g of n is going to cover the lower bound in omega. Likewise, for theta notation, it's going to be f of n is, so f of n is going to sit between two values, so it says c1 into g of n, because that's the average case time complexity, right? Less than equal to f of n, less than equal to c2 into g of n. Now this is the average complexity or the average running time, and this is when you say that f of n is equal to theta of g of n, okay? And graphically this will look like, right, this is your, let's say, f of n, this is c1 into g of n, and this is c2 into g of n, right? F of n, c 1 GFN. I'm not sure, this notebooks is very bad, whatever I'm using here, but you get the idea. I have a very bad handwriting as well, but just wanted to represent graphically and show you how these functions will look like. So this is going to be the theta representation in a graph, right? So these hold significance based on the input size, and most of the time we consider the big O notation because that is the worst case time complexity, and that's how asymptotic notations work. And we also have certain predefined values for certain algorithms. Let's say if an algorithm is O of n, we call it as linear time. If it is O of n square, there is something called O of n square. There is O of log n, which is logarithmic time. Okay, then there is big O of n log n. Certain algorithms take this much amount of time, certain algorithms take this much amount of time. This is n square is going to be quadratic, right? So all this delves from the fact that, for example, I did this simplification, right? This is how it is usually simplified. So n square might also be a function like 3n square plus 4n plus 1 or whatever it is. It roughly translates to n square for very large values of n. So that's how it's represented here, and we have more definitions such as exponential representation, which is 2 power n, right? So all these are different time complexity measurements for different algorithms out there, and we're going to take a look at some of the algorithms that have such time complexity. We're going to calculate the time complexity and space complexity of the algorithms that we're going to take a look at. I'll also teach you how we can calculate that, but that is going to be another video. So that's it for this video. If you liked it, hit the like button, subscribe to CodeWithAni if you haven't already, and I'll see you guys in the next video with some detailed examples. Bye bye.